In this video, we're going to be doing some practice problems for work energy, power, linear momentum, and also rotations in physics. So for our first question, a force of magnitude F is being exerted tangentially to the edge of a horizontal disk of radius r as shown in the figure. The force is exerted over a time interval delta t, during which the disk rotates through an angle of pi over 2 rad. So it's going to go an angle of pi over 2. That's what's going to travel. So what is the change in the angular momentum of the disk during the time interval delta t? So your answer here is going to be using torque. So torque is equal to the force times the lever arm. Here R is going to be your lever arm, and we know sine of 90, the angle that it's exerted at is 90 degrees, sine of 90 is 1, so we don't have to put that there. So work is equal to torque times theta. So work, you can replace in the formula torque with FR, and you can replace theta with pi over 2. Work is equal to delta K. And also, you know that delta L is angular momentum, and torque is equal to delta theta. Torque is equal to FR, and you can have torque times delta theta, and you should sub in your torque that you had earlier. So you have your torque here, that you got over here, sub that in, and then that's going to be your answer. So for this, they're kind of trying to trip you up because you don't really need to have theta, because if you look at the formula for angular momentum, there is no delta theta inside of the formula. It's just dependent on inertia and omega, so you don't need that. So your answer is just going to be the change in angular momentum is force times r, your radius, times delta t. So that is going to be option D. Now for your next question, you have the graph represents the net torque exerted on a disk as a function of time. The disk rotates about an axis through its center. At which of the following two times is the angular momentum of the disk the same? So what you need to know here is that in this graph, the area under the curve is going to be what angular momentum is. So that's the area underneath the torque versus time graph. So here, in order to calculate what angular momentum is, you need to know that the net area between two times is equal to 0. That will be the angular momentum of those two times. And that's when you have the net torque is equal to, or you have your net angular momentum is equal to 0. So what you're going to do is you're going to look at each of these components of the area under the curve. And when we say under the curve, you basically are looking from this line here. You're looking at what the area is from that line to the x-axis, from wherever it's extended to. So here you're looking at a triangle, a square, a triangle, a rectangle, a triangle, another triangle. So you split those up, and then you take base times height, or you take 1/2 base times height for those, and then you calculate what the area is in each of those intervals. After that, you need to find what delta L is. Delta L is the cumulative area change. So initially you have 0, because we know we start from the origin, and then at L1 it's equal to 1, because we have 1 minus 0. So, and then at L2 you have 1 plus 2, then L3 you have 3 plus 1, which is 4, and then L4 you have 4 minus 1, because we have a negative area, so you subtract. So what we can see here is that when you have the areas of 2 and 4, they're going to be the same. So 2 and 4, they're the same. Now for our third question, two rotating objects A and B have equal rotational kinetic energies. Object A has rotational inertia I, and object B has rotational inertia 2I. What is the ratio of the angular momentum LA over LB of the two objects? So K rotational is equal to 1/2 I omega squared. IA is equal to I, and IB is just double that, 2I. So what you're going to do is you're going to take your K rotational, you're going to make an equation with that, and you're going to set them equal to each other, and the only thing you're going to change really is what the I is. You're going to substitute in your I's here and your IB here. So this is 1. So you can just cancel out that 1/2 and the I's, and you're left with this. You take the root and then you simplify it. You just take the ratio of what they are over each other. Here we have our ratios here. We can see that L is equal to the root of 2ik rotational. That's because the rotational kinetic energy of both the objects is the same, and the angular momentum of each object will only depend on the rotational inertia. And here specifically, the angular momentum will be proportional to the square root of that rotational inertia. So that means that object B has twice the rotational inertia as object A. So its angular momentum will be a factor of root 2 greater than object A, which we can also see in the ratio here when you see what is left over when you just divide. So you cross out 1 omega V and you just keep crossing out, that's what you get. So for our next problem, you have this scenario where a block is placed at the bottom of a semicircular track as shown. Then an identical block released from a height h above the track slides down and collides elastically with the block at the bottom of the track. Then the block, so it's going to go down after this, and then the block is going to slide up the track, and then it's going to reach a maximum height, h max. So that's the second block. This block is then going to go up like that. So this is first, pink will be for scenario 1. It'll crash, and then it goes up, and then it will slide down. So now in scenario 2, it's repeated, but this time they're going to stick together so you can have a stick. This one you just had 1. So they're going to stick, and then they're going to go up. So now you have double the mass that's being slid up. So we want to know what's the difference in the maximum height that they're going to reach. So we're going to have to list out everything we have. What we have is that if the block starts from a height of h, right, we have gravitational potential energy at the top. It's going to become kinetic energy at the bottom. And we have no mention of friction here, negligible friction, which is the absence of it. So you can just say UG is equal to kinetic energy. So that's going to be now let's look at scenario 1 in more detail. So in scenario 1, the top block will stop and the bottom block will continue with the same speed that it had, and the top block will immediately keep its same speed that it had before the collision. Therefore, the bottom height will reach its height h max is equal to h. But how do we get this? Well, this scenario was an elastic collision, and we know that the blocks have the same mass. So when you have an elastic collision where blocks have the same mass, this is gonna cause your velocities to swap. So that means that your moving block at the bottom will have this speed of v is equal to the root of 2gh. Now, what is the height that is reached? So let's use a different color. We know that when it's reached its height, it's going to have all of the kinetic energy, and it's going to convert back to potential energy. So you can take your v and you can square both sides here actually, and that's going to become v squared is equal to 2gh. So if you sub that in, then in your scenario up here, you can take that v squared and you substitute that in there. So that's going to become h is equal to h, because you have mgh is equal to 1/2 times m times 2gh. So that's where you get h is equal to h. Therefore, h max is equal to h for scenario 1. Now, what about in scenario 2? This is when you have an inelastic collision. It's a perfectly inelastic collision. So that's when they stick. So we can use conservation of momentum. So we're going to start off with what our initial momentum is. and make that equal to our final. So that's mv. And our final mass is 2m. We have vf. So your vf is equal to v over 2. Now we want to find the kinetic energy post the collision. So kinetic energy final is 1/2 2m. We have our vf, which is v over 2 squared. But our K initial was equal to 1/2 mv squared. So if you see what the difference is between these two, is that if you have Kf over K initial, that's equal to 1/2 2m over v squared over 4 divided by 1/2 mv squared. So we can see that if we cancel out our stuff, we see that 1/2 of the energy is lost in the inelastic collision. Half of the energy is lost in your inelastic collision. So now you have to convert your remaining kinetic energy into height. So that's your leftover kinetic energy that's going to go into the height that's reached. So after the collision, the two blocks, they are going to climb the track. They go up. They went up to there. So you have 1/2 2m. Vf squared is equal to 2m gh. You have Vf is equal to v over 2. 1/2 2m v squared over 4 is equal to 2m gh. So what you have here is mv squared over 4 is equal to 2mgh. You can cancel out the m's and you get v squared over 4 is equal to 2gh. We also have that, so what we did here was we substituted in vf right here. And what we're going to do now is we're going to take v squared and we're going to substitute that in right here. So v squared is equal to 2gh. So if you sub this in, you are going to get 2gh over 4 is equal to 2gh. Gh over 2 is equal to 2gh, and h is equal to h over 4. Now, we want to compare this with h max. So we know h max earlier is equal to h. So h is equal to h over 4. And h over 4 is less than h over 2. So that means that the height you reached for the scenario 2 is going to be less than 1/2 of h max. This is for scenario 2. So overall, you need to remember that we had here a perfectly inelastic collision, and in these types of collisions, you have a loss of kinetic energy. So if you have a loss of kinetic energy, that will mean that there is going to be a loss of UG that's reached because there is no friction. So whatever you have as your kinetic energy will be converted into your potential energy. But if you had less kinetic energy to begin with, you have less potential energy that you'll reach ever. So because our mass, we doubled it and there was energy loss, that means the height becomes 1/4 of the original. Now for our next question, we have a system consists of two identical carts that can slide along a rod of negligible mass. The system rotates with negligible friction about an axle at the center of the rod. Initially, each cart is fixed halfway between the axle and the end of the rod, and the system rotates with an angular speed omega initial, as shown in the top view. While rotating, the carts are released to slide to the ends of the rods. Which of the following correctly relates the final angular speed omega f to omega initial? So what we're going to do is we have no mention of, let's see here, negligible friction is going to be what we have. So that means we have no net external torque, no friction. So that means we can say we have conservation of your angular momentum. So L initial is equal to LF. L is equal to I omega. So now we want to assign the distances. So let's let the distance from the axle to the rod end equal to R. So we can see that the carts initially, they are fixed halfway between the end and the end of the rod. System rotates with angular speed. So initially carts are halfway to the end. So our initial is R over 2. And then we have that final B. You have RF is equal to just R. Now, what is the moment of inertia formula? Here we have a point mass, which is what we're going to consider this to be. So we have I is equal to the summation of the masses R squared. And we have for our masses, we have two identical cart masses M. So what you have is, for your initial moment of inertia, you are going to have, let's make some room here. I initial is equal to mr over 2 squared plus mr over 2 squared. I initial is equal to 2m r squared over 4. And I initial is equal to 1/2 mr squared. Now for our final, you have IF is equal to mr squared, because initially, again, let's highlight these. You have r over 2, which is why you substituted it in there. But then finally, we have it's extended to the full r. And you're going to have plus mr squared again. That's going to equal to 2mr squared. Now, let's apply this to our momentum conservation. So now we have what I is, right? Our initial I. So I'm going to put this here. And we also have our IF. So what we can do here is you can cancel out that mr squared, and we'll write what we have next. 1/2 omega initial to omega f. Omega f is equal to omega initial over 4. The moment of inertia increases, and what that means is that moment of inertia is a measure of how resistant something is to a rotational change. So if you move all your mass to a larger lever arm, that means it's going to be harder to rotate. If you have a solid disc versus a mass or a shape where all your mass is at the rim, the solid disc is much easier. because the mass is closer to the center, like when you have a figure skater. So that's why your moment of inertia will increase as you go outwards. And for us to be able to conserve that angular momentum we have, because of the fact that we don't have friction, that's how we know we have angular momentum. We know that the angular speed has to decrease to compensate for this. That's because if you change one thing in the variable, L is equal to I omega. So increase L, or you increase I. No, let's keep L. This is going to be constant, right? So that means you have to increase I and you have to decrease omega. Or another option would be you decrease I and you increase omega. So either or, if you want to keep the same L. So that means that omega F is going to equal to omega initial over 4, which is what we got here. So we can just erase this and we can highlight our answer. That's going to be option C. So here IF is 4I initial. So that's why omega F is omega initial over 4. Now for our next question, we have this rotating platform. A child is standing at the edge of a rotating platform as shown in figure 1. The child's platform system, so the child and the platform are included in this system, is rotating with negligible friction around a central axis. The child then slowly walks directly to the center of the platform as shown in figure 2. Which of the following correctly states the change, if any, of the angular speed of the platform as the child walks to the center of the platform? So no friction means that you have no external torque, aka you can just say summation of torque is equal to 0. Then you have conservation of angular momentum. So what in these two figures is changing? The only thing that is changing is the child's position. So the child just moves inwards. So what is that? That is a change of R. So what is changing in our angular momentum formula? This is changing your I. Your I is equal to mr squared. And your R is the thing that's changing. So I is going to be proportional to radius squared. So that means that IF is less than I initial. So in our conservation of angular momentum, we have, let's actually put this over here to have more space. So we have IF is less than I initial. So omega F has to be greater than omega initial. So that means your angular speed is going to increase. The reason is, again, think about the figure skater pulling their arms inward. So your rotation is going to speed up when the mass moves closer to the axis. It's the same thing as the compensation. So a rule you can write down is when you go inward, when mass moves inward toward axis, and also when mass moves outward a disk with rotational inertia of 1.8 kilograms times meter squared is rotating counterclockwise about its center with an angular speed of 6 rad per second. A second disk, which has a rotational inertia of 1.2 kilograms times meter squared, is rotating clockwise about its center with an angular speed of 6 rad per second squared when it drops directly on top of and sticks to the first disk. The two disks then rotate without slipping. What is the new angular speed of the disks? So here that was too. What you're going to start off with is looking at what is your moment of inertia. So here we're given what the rotational inertia is of the disk and also its angular speed. Here we also have rotational inertia and speed. We want the new angular speed of the disks. And we have a stick. We have no slipping. And they stick together, so you have no external torque. Clockwise is going to be negative. So for disk 1 and disk 2, we're going to write these out. So let's write that Li equals Lf here, so we can show that below. And this result is positive. When you have 6, use this formula. When you have the opposite direction, you subtract your angular momentums. You could also represent this as one string like this. So for our next problem, an acrobat is initially hanging from a bar over a platform of negligible mass attached to a spring as shown. The acrobat then releases the bar and falls to the platform. When the acrobat lands on the platform the acrobat moving until they momentarily come to rest. So we want something that is going to indicate when does this system have the largest mechanical energy and why. Has been done. When your acrobat has fallen the greatest distance. AKA when you are at max spring compression. And that is when your V is equal to 0 and your spring potential energy is equal to its max. So all work done by gravity has been stored in the spring. Immediately after, because the acrobat is the greatest distance from the lowest point of the motion and has the greatest amount of gravitational potential energy. No, because although the gravitational potential energy relative to Earth is the largest here, Earth is not a part of the system. So this is not the system's actual mechanical energy. Earth not in your system. So immediately after, the acrobat releases the bar because the spring is at its maximum length. Spring length does not equal to mechanical energy. When the acrobat and the platform come to rest, because the acrobat has fallen the maximum amount and all its work done by gravity on the acrobat has been converted into potential energy in the spring. Yes, because when you're at the maximum compression, the acrobat has fallen the greatest distance, meaning that the gravity has done the maximum amount of work on the system because it can't be compressed any further. So that means, yes, that's when your mechanical energy is the largest. So that's going to be C. Now let's just look at D. When the acrobat and the platform come to rest because the spring has transferred all of its energy into the acrobat. No, because the spring, it does not transfer energy into the acrobat. That's wrong. The energy is stored in the spring. So let's see. For our next question, an astronaut on a space station throws a ball of 0.3 meters towards the wall. The ball travels in a straight line over a distance of 1.0 meters before colliding with the wall. Immediately before hitting the wall, the ball has a kinetic energy of 1.5 joules. The wall exerts an average force of 5 newtons during the collision, after which the ball rebounds with a kinetic energy of 1 joule. By how much did the internal energy of this wall system increase during the collision? So what is our mechanical energy before the collision and after the collision? Mechanical energy pre, mechanical energy post. So loss of kinetic energy is going to become heat, deformation, sound. These are all going to be internal forms of energy. So internal energy is increased by that 0.5 joules. So that's just A. Now, for our next question, we have this. A sled is released from point A on a track where the friction between the sled and the track is negligible. Point A is at a vertical position of y is equal to h initial, as shown. The sled remains in contact with the track as the sled passes through points B and C. Let system A consist of only the sled, and system B consists of the sled and the earth. Which of the following correctly indicates at which point, if any, the mechanical energy E of the system is at a maximum? So what is our mechanical energy here? Mechanical energy is going to be equal to K plus U, but that's just general. But whatever we include in potential energy is dependent on what our system is. So let's write out what our systems are in detail so we remember. Now, what happens during the motion? So during the motion, the sled, let's do this up here where the sled is. During the motion, the sled goes down, so it's going to go down, and then when it goes down, that means kinetic energy increase. So you have maximum energy at point B. Kinetic energy max. Now, what about system B? This is for system A. For system B, no, not this one. Let's use this color. So for system B, this is when you have sled and the earth. So FG is going to be internal, and friction is going to be negligible. So that means that the only forces that you have are going to be the internal forces. Only your internal forces are going to act. So mechanical energy is conserved because this is stuff that's inside of the system. Energy is not ever lost to something that is outside of the system. What energy loss means is that your energy is lost to something that's not in the system where you can withdraw that energy from and keep transforming that energy within it. But here, the energy only transforms to different forms, so it's conserved. So energy is constant everywhere. So for system A, your maximum is going to be when you're at point B. And for system B, everywhere your energy is going to be constant. So your answer is going to be where that is stated. And that's going to be C here. A ball of mass m is loaded into a launcher with a spring of spring constant K. The ball is pushed down until it is at a vertical position y is equal to 0, and the spring is compressed at a distance delta L as shown. The ball is then released from rest. Immediately after leaving the launcher, the x and the y components of the ball's velocity are vx and vy respectively. The ball reaches a maximum height of y max and lands a horizontal distance delta x away from its initial position. Energy losses due to friction are negligible. Which of the following is the correct conservation of energy equation that compares the total mechanical energy of the ball spring earth system immediately before the ball is launched to the total mechanical energy of the ball spring earth system? So the difference is ball spring earth. So this is before it's launched, and then this is when the ball reaches the maximum height. So let's start out by listing our energies here. We can write that we have conservation of energy because we can write out we have conservation of energy because we don't have friction. So L initial is equal to LF. And also we can start to consider what our kinetic energies are and what our potential energies are. So summation of So our Earth is included. So because the Earth is included, FG and UG is going to be internal. That's why you have conservation of energy. Now, what is your initial mechanical energy? Let's talk about before versus after. Before and after when you're at its peak. So before, your ball is at rest. Ball is at rest. Kinetic energy is equal to 0. The spring is compressed. And UG is equal to 0 because Y is equal to 0. It has no height. UG is equal to MGH. H is equal to 0. Therefore, it's equal to 0. So your initial energy is just going to be equal to 1/2 K delta L squared because your UG was 0. Now, what about here? You can split this. You have Vy, right? So when you are at the maximum point in your kinematics projectile launch, that's when you have a Vy that's equal to 0. And your Vx is going to remain because this is what's going to continue your motion. It's going to continue your motion. But remember, in these questions, you always have an acceleration, and it's always going to be 9.8 meters per second squared anywhere. It's just gravitational constant. So that means your kinetic energy here is 1/2 mv squared. So let's just write the whole thing. Actually, EF is kinetic energy plus UG. So your velocity is going to only be your x component because your y component is 0. And your y max, aka y max and h max, same thing. You're going to be at your highest because this is the highest point of your projectile. Now set them equal to each other because you have your conservation. So that's C. Block 1 of mass M1 is released from rest at the top of a ramp of a height h initial as shown. The block slides down the ramp onto a flat section and collides and sticks to a second ball of M2 where M2 is equal to M1. After the collision, the blocks have a speed of Vf. Frictional forces between the block and the masses are negligible, and the surfaces are negligible. Block 1 is then replaced with a block of mass 2 M1, and the scenario is repeated. Which of the following correctly indicates how the final speed of Vf of the blocks will work compared to their original scenario? So if we have energy conservation, we have that energy conservation. You have your MGH initial is equal to 1/2 mv squared. Your UG is equal to your kinetic energy when you're at the bottom. So your masses, they're going to cancel out. And you're going to get M is equal to the root of 2GH initial. So what we see here is that in this equation, this is not mass, this is actually V. So this has no mass in it. So what your speed is, it's not dependent on how heavy your mass is. It's only dependent on your gravitational constant and also the height that you release your object from. So in the first scenario, we have that. So scenario 1, you have M1 is moving and also M2 is equal to M1 stationary, M1 stationary. So if they stick, we know that sticking means that you have a perfectly inelastic collision. So now what you can do is you can use momentum conservation. So you're going to have your initial momentum and your final momentum. So P initial is equal to PF. So you have P initial is M initial times V, and that's going to be M1 plus M2 VF. So we have M2 is equal to M1. So you're just going to have PF is equal to 2M1 VF. M1V is equal to 2M1 at VF. Just erase that. VF is equal to V over 2. You can cancel out that M1. Now, what about scenario 2? Scenario 2, M of the moving block is 2m1. V bottom is equal to still 2gh, initial the root of that, and then your initial is still going to be 2m1, oh my gosh, 2m1v. So then your final mass final post stick is equal to 2m1 plus m1, which is 3m1. So PF is equal to 3m1 VF. Now set them equal to each other. You have your P initial and your PF. So now 2m1V is equal to 3m1 m1 VF. So VF prime is 2 over 3 V. Now we can compare our different V's. Finals that we got. So what we see is speed is going to increase, but less than double. It's 1.33. So it's going to be by a factor that is less than 2.